we'll focus on buffer solutions. This is an important section in ionic equilibrium. Buffer solution is a solution which will show a very small change in pH when you add acid to it or you add base to it. Now, if you have a normal solution, which is not a buffer, any solution, maybe water, it may contain HCl, it may contain NaOH. So if we have a solution and we add acid to it, it shows decrease in pH value, and when you add base to it, it shows increase in its pH value. But if you have a buffer solution, on addition of acid, the change or decrease in pH is very small, negligible in most of the cases. Similarly, to a buffer solution, when you add a base, the change in pH value is again negligibly small. We can ignore it in most of the cases. Okay, so a buffer solution shows a very small change in pH when acid is added or base is added or you dilute it. Okay, buffer solution could be of several types. Now, one important category is an acidic buffer solution. Acidic buffer. An acidic buffer comprises of two components, a weak acid and its salt. Salt means conjugate base. As an example, you can see if we take acetic acid and its salt, sodium acetate, this mixture may act as an acidic buffer. Another example, if you take HCN plus KCN, this mixture may also act as an acidic buffer. If we take benzoic acid and its salt, say sodium benzoate, this mixture can also act as an acidic buffer. So an acidic buffer will comprise of a weak acid and its salt, which mainly contains its conjugate base. Like here I have taken acetic acid, so its conjugate base is acetate ion, so salt comprises of this conjugate base. Okay, this is the main component required for buffering action. Okay, so if you have an acidic buffer and you have to calculate its pH, you can use this equation, pH equals pKa of the weak acid plus log ratio of concentration of the salt and the acid and base being 10. Using this equation you can find pH of an acidic buffer solution. This equation is known as Henderson's equation. Okay, let's take an example. Find pH of an acidic buffer solution. The question clearly specifies you have to find pH of a buffer solution. In certain questions, it is not specified that you have a buffer. You have to identify yourself. Okay, we have an acidic buffer solution here which is having these two components, a weak acid and its salt. So to find out pH, I'll use Henderson equation, pH equals pKa value of the weak acid, means acetic acid, plus log, here you write concentration of salt and here you write concentration of acid. Now this is a easy question, all the values are very clearly indicated. pK of acetic acid is given, so you put the value 4.74. Now concentration of salt 0.2, concentration of acid 0.02. So when you simplify, you'll get log 10. The value of log 10 is 1. So answer would be 5.74. This is pH of the solution. Okay, let's take another example. Please see the next example. Here we have a buffer solution comprising of weak acid, acetic acid and its salt. Its pH is specified in the question 4.74. Concentration of acid is given, concentration of salt is required. Again a simple question based on Henderson equation. So I'll use Henderson equation, pH equals pKa of this weak acid plus log concentration of salt divided by concentration of acid. Okay, so we'll put in the values specified in the question. pH is given as 4.74, pKa is also given as 4.74. Okay, concentration of salt is not specified, that we are supposed to find out, and here concentration of acid is given 0.1. So you can see these two numbers, they cancel out and we get 0 equal to log of okay. Now if you know log 1 is 0, so this ratio must be equal to 1. It will give you concentration of salt as equal to 0.1 molar. So salt will have same concentration as that of acid because pH and pKa are equal. Okay, so whenever pH and pKa are equal, this ratio must be equal to 1, indicating salt and acid are having equal concentrations. Okay, let's see another example. Now in this case we have to find pH of a solution, and you can see the word titration. So some titration is carried out here. Acetic acid is titrated against strong base NaOH. So the two are going to react and form salt plus water. Okay, the number of millimoles of acetic acid would be molarity into volume, that gives me 10 millimoles. So I'll write number of millimoles 10. Okay, and volume of NaOH of course varies as you keep adding during the titration, but try to understand. It says find pH when neutralization is 50% complete, half complete. Okay, for complete neutralization of acetic acid you will need 10 millimoles of NaOH to be added externally, and for 50% neutralization you will add half of that. So you'll add half of 10 millimoles, means you'll add 5 millimoles. So if you look at the values, NaOH being in smaller amounts would be limiting reactant. So it will be completely consumed and it neutralizes 5 millimoles of acetic acid, which implies 5 millimoles are left, which are not neutralized as NaOH is added in lesser quantity. Okay, so 5 NaOH millimoles on neutralization, they produce 5 millimoles of the salt. So final sample contains these two things, a weak acid and its salt. So a buffer is generated. Okay, initially it wasn't a buffer, but buffer was generated. So it's not a direct question on buffer. You have to see the type of reaction which leads to creation of a buffer, a mixture of weak acid and its salt. So now we can use Henderson equation to find pH of this buffer solution. pH equals pKa plus log concentration of salt divided by concentration of acid. So I'll put in the values. pKa of weak acid, acetic acid is 4.74 as we have seen in the previous two questions, plus log concentration of salt would be 5 upon volume total, and concentration of acid would be 5 upon volume total. Now these two numbers are equal, they cancel out and we get log 1, and log 1 is 0. So pH would be equal to 4.74. Okay, we'll see more in the next lecture. Thank you.